Acids Bases Equilibrium Part 2. Today we will be discussing weak acids and bases and some equations relating to them and solve a couple of problems. What's the difference between a strong acid and a weak acid? Strong acids have very large Ka values. They are almost 99.9% dissociated. Here are some examples: HClO4, H2SO4, HNO3, HCl, HBr, HI, and I already asked you to memorize these values. Weak acids have small Ka values. The dissociation is less than 50%. Here are some examples: sulfurous acid, carbonic acid, HF, and acetic acid. Difference between strong base and weak base, very similar. Large Kb values, almost 99.9% dissociated. Some examples are sodium hydroxide, potassium hydroxide. For weak bases, the Ka values are very small. They are less than 50% dissociated. Ammonia is an example of a weak base. It reacts with water to form ammonium ions and hydroxide ions. Ammonia can also be bonded with alkyl groups and form primary amines. Here is an example of a primary amine which will behave like a base. It's very similar in its behavior with ammonia. So I've just included it here. Make a note of it. It behaves exactly the same way ammonia would behave. We had seen dissociation constants for acids. The general equation for the dissociation of an acid. The Ka value can be found by using the expression H positive into A minus divided by HA. Similarly, we can also have a dissociation constant for a base, which we call Kb. Here, the base is represented by the letter B with a lone pair, just like ammonia, for instance, plus water, giving you the ammonium ion. Here it is B plus H. So B has accepted a proton. If you look at it, the base has accepted a proton and changed into BH positive, which means the water has lost a proton and changed into OH minus. So water is the proton donor and the base is the proton acceptor. And we have the conjugate acid-base pairs over here. So this is the general expression that we have here. Kb is equals to BH positive into OH minus divided by B. So anytime you write Kb expression, you will find in the numerator you will have OH minus ions. So that's the indication. Kb represents the concentration of the hydroxide ions. Here you will see the OH minus. So if you are writing an equilibrium expression and on the product side you have hydroxide ions, then that will represent a Kb expression. pKa and pKb, these are two new terms that we had seen. These expressions are analogous to expressions for pH. We derived it to express the concentrations in a more convenient way using whole numbers. pKa is equals to negative log Ka. For pH, we had written pH is equals to negative log H positive. So it's exactly similar to that, with the difference that we are replacing H positive with Ka value. Similarly, pKb is equals to negative log Kb. A smaller value for pKa represents a stronger acid, and a smaller value for pKb represents a stronger base. So we may use pKa, pKb, pH, pOH, Ka, Kb, all of these terms while talking about the strength of acids, and you will have to convert it into the appropriate term for solving problems. So we are familiarizing ourselves with the different equations that we will see in this topic. For the conjugate acid-base pair, this relationship is also true. Kw represents ion product of water, and that's equals to H positive into OH minus. In the previous slide, we had seen Kb represents OH minus ions. Similarly, Ka represents H positive ions. So we can also write Kw is equals to Ka into Kb. There is no need to derive this equation. We can show the relationship though, but we can see the relationship here, how they are related to Kw, and we can use this to calculate either Kb, Ka, or Kw. We can convert one to the other. In certain problems, you may be given Ka value where you will need the Kb value. You can use this equation to actually convert it. So here are the relationships. Kw is equal to K into Kb. Rearranging, Ka is equal to Kw by Kb, or Kb is equal to Kw by Ka. They're just the rearrangement of the first equation. pKa plus pKb is equals to 14. pKa plus pKb is equal to pKw. This is also true. pH is equal to negative log hydrogen ion concentration. pOH is equal to negative log OH minus ion concentration. pH plus pOH is equals to 14. These are some of the expressions that you may want to learn and use it in the problems that are given. So I've just listed them here. Here is a problem for you. We're going to calculate the pH when the Ka is given and some concentration terms too. Formic acid is a monoprotic acid. Formula is HCHO2. The organic form of this equation is HCOOH. This is called a carboxylic acid, or the carboxylic acid group is COOH. But you can also write it as HCH2O, CHO2. Calculate Ka for formic acid at 25 degrees Celsius if the pH of the solution is 2.38. You're given pH. pH is given as 2.38. So keep that value in mind. The concentration of formic acid that is given is 0.1 molar. So we're going to use this information and we're going to calculate the Ka value for this problem. First thing would be to write an equation for the dissociation in water. It interacts with water to form hydronium ions and formate ion. I'm going to write a general expression for this. Ha plus H2O reversibly giving H3O plus A minus. So A minus represents the formate ion. So for any monoprotic ions or monoprotic acids, this equation, the general equation, can be used to write the expressions. So here I've made a nice table. I have the acid Ha, water, hydronium ion formed or H positive, and A minus. The initial concentration we had seen is 0.1. We have no products. With time, there is dissociation going to take place. And the change in concentration is minus X, X, and X. Coefficients are 1 and 1. But we don't have the values here. Now what you're given is the pH. The pH is given as 2.38. We're going to use that to calculate the molar concentration. That's what we're going to do. So we know that pH is equal to 2.38. The H plus ion concentration is calculated using the equation 10 to the power of negative pH, which means the hydrogen ion concentration is obtained to be 0.0041, which means the value of X is the concentration of hydrogen ion, which is equals to 0.0041. So I actually have a number for X, and that number is 0.0041. And because I have that number, I also have the number for A minus, which is the same. And we know how many moles of the acid had dissociated to give us this. Therefore, there is a decrease in the same amount. So original concentration I minus C is equals to 0.095. This is the value. I've got the equilibrium concentration of hydrogen ions from the pH. I've got the concentration of the anions. Write the equilibrium constant expression now and then solve for it by substituting the numbers that you obtain right now. Ka is equals to the concentration of hydrogen ions into concentration of the anions divided by the number of moles of undissociated acid which is present over here. The value of Ka is 1.75 into 10 to the power of negative 5. Here is a second problem for you. We're going to calculate pH from Ka. The concentration of vinegar, acetic acid, was found to be 0.75 moles per liter. Calculate the value of hydrogen ion concentration and pH for this acid. If Ka for acetic acid is given as 1.8 into 10 to the power of negative 5. The first thing, we wrote an equation for the dissociation in water. I made a general expression using HA, so it's easier for writing. Made an ice table. The initial concentration is 0.75 that's given to me. So change in concentration is minus X, X and X. Equilibrium concentration would be I minus C, which is 0.75 minus X, X and X. So this is the information that we have. So we're going to use this information and we're going to determine the value as required. Let's see what we can do with this. So the ice table is again here. The Ka expression for this reaction is Ka is equals to H3O positive into A minus divided by HA. I'm going to substitute the values in the equilibrium constant expression over here. X and X, they go here. And in the denominator, I have this value going over here. The value of Ka was given 1.85 into 10 to the power of negative 5. And that's equals to X squared divided by 0.75 minus X. Now in this case, the value of Ka, 1.8 into 10 to the power of negative 5 is extremely small. So the value of X, as we have done in the equilibrium problems, is very negligible in comparison to 0.75, the original concentration of the acid. So for practical purposes, we are going to neglect this value for X and we're going to do a calculation here. That's what we're going to do here. So we're going to solve for X. X is equal to root of Ka into 0.75. Ka is 1.8 into 10 to the power of negative 5. So into 10 to the power of negative 5. And that will give you X as 0.0038 moles per liter. Now you have a value for X. So here is the value for X. That is the molar concentration. And X represents the hydronium ion concentration, which means we can determine the pH if you have the molar concentration, which we just calculated. So pH is equal to negative log 3.8 into 10 to the power of negative 3, or pH is equals to 2.43, and that's the final answer. So we can calculate the pH of a solution if Ka is given to you and the initial concentration of the reactants are given. So we have done two problems. One, you calculated the Ka from the pH, and the second one, from Ka you calculated pH. There are a number of problems for weak acids and weak bases based on this argument. That's it for now for this part 2 of the lesson, where we looked at the different equations that we need and we solved two problems. There will be more problems coming using these equations. We will see them as we go along. That's it for now.